Morning, everyone. So we've been looking at waves in our chapter so far. We've been introducing concepts of wavelength, frequency. Lately, we've just been looking at how waves interact with different media. So if the media is not very optically dense, if the n value is fairly small, the wave can pretty easily get through it. While if the n gets higher, especially with that marching band analogy, as the different sides of the marching band actually slow down, it actually causes the wave direction to actually bend. So we're just going to flesh it out a little bit more here. We ended off with sort of Snell's law. That was a really important relationship for us here. So Snell's law, this was both for reflection as well as refraction. It basically said for us here, the n1 of sine theta 1 is equal to the n2 of sine theta 2. So basically, depending on the optical densities, depending on the media, how hard it is to travel through, that's going to have an impact on what happens to your thetas. That influences the angle that it comes in versus the angle that it goes out at. So far we've been looking at pictures like for a reflection kind of question, we have what's called the incident ray. Again, important for you to remember is we always measure things relative to the normal. So 0 degrees here would be the perpendicular line. The incident angle is the one that's oncoming. And in this one here, reflection, as we'll see in today's lesson, the mirror is the typical device for a reflection. We expect things to basically bounce off exactly at the same angles that they came in at. So this angle ends up leaving. We call it a reflected ray, and then we had a theta 2, and theta 1 equals theta 2, or you can say theta I equals theta R. The case was a little more interesting when we did refraction. For refraction here, we had light actually going through surfaces here. I gave you the example of, let's say you're standing at the bottom of a swimming pool for some reason. If you look straight on, if you look perfectly along the normal, although you as a source here might set the beat, set the frequency here, it may be a lot easier for the waves to actually travel out here. If it's 0 degrees on, it's going to be 0 degrees off. But more sort of interestingly here is because we are going from relatively, let's say in this example, we're going from water with 1.33 and air which has a value of 1.00, what's going to end up happening is going from hard to easy, the refracted ray actually bends away from the normal as given by exactly the same formula. So what I'm picturing here is as you're looking outwards, right? So maybe, again, I'm using the simplification here. Imagine you're like Cyclops and you're actually generating the light source. We're actually going to see this is actually the opposite. The light is actually somewhere out here and is actually bending through the normal and reaching your eye, but just for simplicity, it's coming out this way. Let's imagine that marching band analogy here. At first, we're in the water, so it's really too hard to travel through. The parts that run into the boundary first are going to be this side of the marching band. They end up speeding up. The other guys in the water have no idea yet. These ones here end up speeding up, and we end up getting not only the wavelengths may be farther apart, but the direction that we end up traveling is actually going to be a little bit different from what we went in it. Sometimes they do try to trick you and they try to give you the angle with respect to the surface, but remember to always calculate the angle. This is going to be theta I, and this is going to be theta 2, and basically the marching band will eventually head off in some direction. When you have your formula, sort of V is equal to F lambda, a couple important notes here. V depends on the medium. It depends on what material you're traveling through, whereas the frequency is set by the source. Frequency is whoever's generating the beat, whether we're in an easy medium or a harder medium here, that doesn't change. I mentioned specifically sometimes the math here gives you an error, and basically it's the idea because, especially going from hard to easier medium, because we are bending away from the normal, there is a very special angle. Let me just draw another diagram of this. There is a very special angle referred to as the critical angle. And they don't need to define this any more than that, but just make sure you know critical angle, basically the refracted ray, the ray that's trying to leave the surface. The refracted ray leaves parallel to the surface. So therefore your theta 2 is equal to 90 degrees. So imagine we're sending in a ray. This critical angle will be different depending on what medium that I'm at. So far I'm 1.33 and air is 1. Basically, on the other side, we're bending so far away from the normal that we just managed to eke out. We just managed to go parallel. In that case, they're measuring from the normal. This one here is going to be at 90 degrees. So we did that calculation for water. I think critical angle was about 48, 49 degrees or so. You can verify that. And basically what happens after if I look anything beyond the critical angle, if I look at an angle that's larger than that critical angle, essentially we're bending so far away from the normal that light ray can't actually escape. It actually ends up bending back downwards. We get a phenomenon called total internal reflection, or TIR. We end up getting reflection instead, which is theta 1 equals theta 2. So if you've ever done any swimming, you probably noticed this here. If you're standing at the bottom of the swimming pool, if you look up, if it's 0 degrees, you can see directly outside. For a good amount of angles, right, you can still manage to look out. You can still see sort of the lights in the roof and all that. But there is sort of a special critical angle that if you start looking too big of an angle, you end up seeing the shimmery of the surface. You can't actually see through. It might be surprising to you. Water should be transparent, should be able to cut through, and it's just that the light rays can't actually escape. What you see as a shimmery sort of watery surface is actually a reflection of the bottom of the pool. When the lights here are shining on this pool here, it's making the floor really bright, and basically that brightness on the ground is actually what you're seeing as a shimmery of the surface. You can no longer see outside the water because that light ray can't actually escape anymore. Remember, you only have a critical angle if you go from hard to easy, and that's because we're going to bend away from normal. If you go easy to hard, you can bend as close to normal as you want. You can even bend on the normal. That's perfectly fine. It'll get through. So if we're going from hard to easy, if we have a bend away from normal, so try to make my writing look better, bend away from normal, that's the only time we're going to have a critical angle. And really all you need to set is basically this is the maximum angle that you're looking out at, so that the angle when it leaves happens to be a 90. It happens to be exactly on that axis there. So we're going to use some of these concepts here on optics, this Snell's law here, but we're going to apply it to two different optical devices. So this one here is sort of an application, still the same chapter on waves, but we're going to look at the application into the optics section. So what we're going to do here for this optics here is we are going to look at sort of light, and we're going to look at how light interacts with different devices. We're going to start off looking at mirrors. What I'm going to do with you is I'm going to show you the different types of mirrors, introduce some terms for you this lesson. Tomorrow we'll come back and we'll take a look at the math of some of these variables, and then we'll come back and we'll look at what are called lenses. Lenses do refraction instead, and then we'll also do a lesson on just the ray diagrams, and also where do we expect the image to form, and as well as math on a separate lesson. So that's sort of the direction that we're headed in. For optics, we're focusing on light as an example of an electromagnetic wave, a wave that doesn't need media to travel through, and we're going to sort of use those two optical devices, mirrors and lenses, to guide us in the next section. So for the first two lessons here, we're going to look at reflection. Obviously, reflection means the light ray actually bounces off or bounces back. The light ray does not get through. Again, the optical device that I care about here for reflection mainly is going to be a mirror. Right? So a mirror, so far, when we looked at it, it's a nice and flat surface. Basically, all the light rays coming in end up bouncing back, the light ray going the other way. We saw in an earlier lesson, right? If I have a nice, shiny, we call this one here a plane mirror because it's a flat mirror. Although every light ray as it comes in will bounce off relative to its normal, because the mirror here is perfectly flat here, it's going to actually bounce off in exactly the same ordering it came from. And what we're going to end up with here is we're going to end up with a nice mirror image. We're going to end up with a nice reflection of what we saw. The reason why sort of scratch paper here doesn't really reflect the same image. Scrap paper here, even though it feels smooth, we know there's microscopic little grooves here. That means when the light rays actually strike this piece of scrap paper, there's no telling which way the normal is for that exact part that actually hit it. Theta 1 is going to equal to theta r, but as these light rays here come in, they may actually end up hitting normals on really strange angles. If I do theta 1 equals theta r, I may actually get this scattering. I may get this sort of reflection. Maybe this one here actually ends up hitting a normal, right, flat 0 degrees from that surface there, and it may actually bounce back, and that's what we refer to as straight light. So this one here is just sort of paper. We're going to, in this lesson here, focus more so on a nice, flat, clean surface. So let's talk in general here before we get back to ray diagrams. There's a couple different types of mirrors. This first mirror here, I already referred to. This one here is called a plane mirror. The word plane mirror just refers to it being a flat mirror. And in this case here, we're going to just imagine I have my plane mirror. I'm going to set up vertically. And imagine you are just standing in front of the plane mirror. The object that's actually going to be reflected, we're going to call you the object. what's going to happen here, again, we are not actually sending off light rays, right? You're not emitting electromagnetic waves. Realistically, what's happening here is there's light all around you. There's light that's sort of bouncing off the mirror and bouncing into your eyes. But what we're going to sort of trace is we're going to trace what direction the light rays are, how do they interact with the mirror in forming the image. So far we have the object. A couple of variables for you already is we can call this distance. How far you are away from the mirror is going to be called the object distance. So because it is a distance, I'm going to put D for it, but I'm going to put DO, O for object. You're there. We'll also talk about your height as well. So in this case here, we have our object height, how tall it is. For a plane mirror, it doesn't really seem like, why do we need to do this, right? We expect to see a perfect mirror image, but we're going to use some of these same variables when we start getting to curved mirrors as well. So that's your object. You have object distance, you have object height. What's going to happen here is actually it's just our brains playing tricks on us. Realistically, the light rays always are on this side, right? The light rays here are always on this side of the mirror. Your light rays never actually interact with the other side. But what's going to happen here is if you see a light ray that actually comes sort of straight on towards you, our brain actually plays tricks on us here, and it basically thinks, well, because light travels in straight lines, it doesn't really know that it's just reflection bouncing off. Our brain actually interprets this light beam as having come behind the mirror. So what we mean here, behind the mirror, I don't mean physically like, let's say I'm on this side of the mirror and I walk to the other side. That's not what I'm saying. I'm saying you are looking at the shininess of the mirror, and it looks like there's a whole reflected and mirror image world inside the mirror. And basically, when I say behind the mirror, you are still looking at this surface. But when I see a light ray that's coming out towards you, it seems like this light ray is coming from an image that's actually physically inside the mirror. So like I said, not physically like you walked around the mirror. This is you're looking at the shininess of the mirror. When you see your reflection inside the mirror itself, you end up forming this guy here. I've already been saying this is called your image. You can also have some other terminology here. We can have your image distance. It looks like there is a reflection of you that's somehow in the mirror. That's a DI. It looks like your image this time here happens to be this high. And this is just our brain playing tricks on us here. Let me write this down in words for you here. Our brain interprets light as traveling in straight lines. It doesn't automatically think about, oh, light's actually bouncing off and light actually doesn't get through. What we're actually getting is if I get a light ray that's coming me head on, that must be coming from an image that's sort of inside the shininess inside the mirror itself. So we interpret it. There's basically a reflection of yourself. You can see your hand here. Your image also has that hand here. Basically, our brain interprets any of these light rays here are as coming artificially. I'm going to use dotted arrows here just to show you these are not real light rays. Light can't actually enter the mirror itself. Light is just bouncing on your side, on the real side. And this side here is just all virtual. This is just our brain playing tricks on us. So in this language here, we can call, not only this is the image, this is sort of the reflection inside the mirror, we can call this image here, we can call it a virtual image. When we describe something in virtual here, we're actually saying no actual light rays pass through. Right? Remember, light is supposed to bounce off the shininess of the mirror. Light can bounce off all it wants on this side. We're going to call this side here the real side. Right, you are a real person. Light rays are technically sort of bouncing off you as a person. It's just our brain playing tricks on us, thinking it's actually behind. For a plane mirror, everything is nice and symmetrical. All your normals are perfectly parallel here. So just like we did earlier, we're going to get a nice mirror image of what we had before. For a plane mirror, we're going to have DO, the object you are in front of the mirror, as matched up to DI. If you look like you're 1 meter from the mirror, it looks like that image that our brain sort of creates for us here. It looks like it's 1 meter away. If I start walking away from the mirror, if I'm 10 meters from the mirror, it looks like the image is now 10 meters back. The DO is equal to DI, and similarly, the HO is equal to the HI. Because we are a flat mirror, we don't have any curvature on the mirror. We end up seeing whatever height I am outside the mirror, it's going to be the height that I'm inside the mirror. So really, the reason why we end up seeing virtual images here is just our brain playing tricks on us. We just thought of light traveling in straight lines. Oh, it must have come from behind when realistically there actually is no light rays actually going through there. Sorry, I just noticed HI here, we're going to call that the image height because that's the height of the image. That's the height of this artificial line. We did that earlier here with our sort of spearfishing analogy here. Remember, realistically, the light ray, because it's going from water into air, it's going to actually be at some angles beforehand, and it's actually going to bend away from the normal as it strikes your eye. Our brain, again, just interprets it silly enough. Our brain thinks, it doesn't remember this sort of refraction. Our brain thinks light travels in straight lines, even though realistically the fish is not here. Where you see the fish, you think, oh, it's right in front of you. In fact, the fish is actually, so this is the real fish. This is sort of like the image of the fish, sort of where you think you are. In this case here, our brain, again, just naturally, oh, yeah, light travels in a straight line, and it sort of gets that wrong. So that's the case of a plane mirror. I've introduced some of the language for you. We say real is where light actually passes through. Virtual is where light doesn't pass through. We have DO, HO, and whatnot. It's a lot more interesting when we start adding some curvature to the mirrors. So plane mirrors. Let's look at curved mirrors. There's two main types of mirrors. Let's talk about them in general, and then we'll come back again and we'll take a look at what are called ray diagrams to predict if I'm standing this far from the mirror, what happens to my image on the other side. For a curved mirror, we're going to look at two types of curvature. One is called a concave mirror. The other is called a convex mirror. Right. So both this word here, concave and convex, refers to the curviness, the bentness. The way I think about it here is when I'm looking at the concave side, it's like me standing here and it's like me looking into the entrance of a cave. So a concave mirror has me, like we just drew here. The concave mirror has me. We're going to be using like a candle. Right? A candle actually releases light. We're not Cyclops or anything like that. So we're standing this side. A concave mirror actually is going to be bending towards you. It's like you're looking into the mouth of a cave. A couple more terminology for you here. We're going to call this sort of middle axis. This middle part where it actually interacts with the mirror. We're going to call this the principal axis. This is the main axis that we're going to be measuring from. Depending on the curvature, how bendy this concaveness is, we're going to use a simplification. Let's imagine that it's perfectly circular. Let's imagine that this ended up making a nice circle. The center of that circle is going to be a point called C. We're going to call that point there the center of curvature. This one would have been the middle of the circle that was left over by this curvature, by this bendy here. And what's going to happen is we're going to separate. There's the center, there's the side. This one here would be a radius. We're going to have halfway, and we're going to have a special point here called the focal point or the focus. So this is called either the focal point or just simply here, this is called the focus. And we're going to see with our ray diagrams why that becomes important. So here you are, you may be standing there or you're setting up a candle. And this time, instead of the mirror being flat, this time it's actually bent towards you. In this case here, what I want you to just remember for a concave mirror for the time being, a concave mirror is a converging mirror. Converging has the notion that light waves comes together. Light rays bend towards each other. So what's going to happen here is as I shine a bunch of light rays here, we're going to do this in more detail very shortly here, but no matter which light ray ends up hitting, they're going to end up bouncing back. They're going to end up converging together. They're going to end up coming together. So that's what we mean by converging. You can definitely, in this experiment, we can play around with how far away I am. I can stand on the center curvature. I can be between F and C. I can get up right close to this curvature as well. I can end up moving, but the center, the focus, and this point here, which we're actually running into, is called the vertex. Those points there are fixed because the curviness of the mirror is fixed. Let me just introduce to you on the other side then. We have the same principal axis, the main axis we're going to be measuring from. This time I'm going to look at the convex side. The convex side could be the back of a spoon, if you like. So this is the front of the spoon, this is the back of the spoon here. In this case here, we still have the same definitions. We have our vertex, right? That's the point where the mirror intersects our principal axis. We have our center of curvature, the center of what would have been our circle. And then we have our focal point, focus. And basically this one here is going to be half the distance to that center there. In fact, there's another name that we can do, not only labeling the F and the V here, we can call this distance here, we can call that the focal length. And that is, as shown on the diagram, this is the distance to the vertex. Or let's even say distance between, so I'll write better here, distance between the vertex and the focus. Right, so the focus is just a singular point. The focus is just that spot sort of midway between the center and the vertex, but that's going to be in between the vertex and this focus point. We're going to use the relationship that the focal point here is going to be 1/2 of the distance to the center of curvature. So the center of curvature is, let's say, 10 meters. The focal point will be 5 meters. Right? In this case here, what I want you to know here is for a convex mirror, not only convex is the bulge is towards you. For a convex mirror, our wording here is it is a diverging mirror. Light rays that end up hitting this not only reflect back, they end up bouncing off, they end up spreading farther away. So light rays coming off this way, they end up separating versus it coming together. So diverging, this one here means they end up separating. That's going to become important later on for our math, so just be careful. You know, converging means comes together. It's the concave for a mirror. Convex, the bulge is bulging out towards you. That's when the light rays actually end up separating. When we fast forward to lens a little later on this week here, we're going to also have a converging lens, lens that actually brings things together, a lens that actually diverges things, but the shape is actually the opposite. A concave lens actually does diverging, whereas a convex lens actually does converging. So careful and definitely know which way these curvatures are. Does it bend towards me? Does it bend away from me? But also make sure you know which ones converge and which ones diverge. We're going to end off this lesson here looking at what are referred to as mirror ray diagrams. Right? And essentially what we want to do is we want to be able to predict if I stood a certain distance, if I was on C, if I was closer than C, I want to predict based on the ways the light rays are actually bouncing off, whether they are converging or diverging, where might I end up seeing my image? Where might my brain actually interpret, oh, light's actually just coming to my eyes in straight lines? Where might my brain thinks, when I look at the shininess of the mirror, when I look at that sort of virtual world that's inside the mirror, where does it look like my image, my reflection actually shows up? And especially if you ever played around with any curved mirrors, you wouldn't be surprised to see sometimes your image is larger, sometimes it's upside down and whatnot. We can actually predict that using these ray diagrams. So having another look at these ray diagrams here, we're going to start off with our first mirror, which is our concave mirror. I'm looking at the opening of a cave. This one here was the one we said earlier. This is our converging mirror. This is our mirror when the light rays were actually coming together. For a ray diagram here, without getting confused and sort of showing too many lines and coming together, turns out we actually only need to draw 2 lines. And based on where those lines intersect, I can actually figure out where my image is going to show up. For this stuff here, it is important for you to use a ruler, so just make sure you pull out a ruler for there. Let me just label some of the important points here. Let's say your vertex, let's say your center of curvature, your focus point. If the spoon here is bent in more bendy, the center of curvature would be different. The focal point would then adjust itself. But let's say that's what I have. This time I'm going to place my object. This time I'm going to make it a candle. Candle is nice because it does actually emit light. Light actually goes in all sorts of different directions. As I mentioned for a ray diagram, you need to know to draw 2 lines. Right? So right now my candle, it's actually farther than the center of curvature. You're going to, using a ruler, for your ray diagram, you're going to draw these 2 lines. A parallel ray. So if I draw a ray that sort of parallels our principal axis, this sort of flat line, a parallel ray converges, it comes together, that's just reminding you language, converges through the focus. So for just this type of mirror, what you're going to do is you're going to take a ruler, you're going to draw a nice straight line. Because we know this mirror here in general converges things together, what's so special about this focal point is, in fact, all parallel rays actually cut through the focal point. Remember, the focal point is going to be halfway to the center of curvature. No matter if maybe it's a taller candle and it sends a light ray earlier, all parallel rays end up focusing through the F. That's why we call it the focus. So that is one ray I definitely want you to draw here. You'll notice I drew it with a solid line because this is a real light ray. Our actual light ray travels straight on, hits the mirror, and focuses through the F there. Second ray here. Again, we just need to draw these 2 rays. The 2 rays for different optical devices will be different, so you need to memorize which rays we draw. But in this case here, the second ray here, even though we do end up having a sort of a curvy nature to this mirror here, the curviness here might actually have our normal at some random angle. There is one special angle that if you hit the mirror head on, that would sort of be like the case, I'm hitting the plane mirror here at 0 degrees, I expect this light ray here to come straight back, even though it's sort of bent on either side. The special point, shouldn't really surprise you here, is if I draw a light ray, again use a ruler, if I have a light ray that goes through the center of curvature, because this is going to be the center and this is a radius here, we're actually having a sort of a perfect circle here. This light ray here will be that 0 degree ray, a light ray that goes through the center and then up, just basically back the way it came. That's just actually going to bend exactly back. So in this case here, a ray that goes through C, through the center of curvature, reflects directly back. That's the only ray that hits head on. It hits the surface exactly at a perpendicular. So I go 0 degrees in, 0 degrees out. Directly, ray through C reflects directly back. Those are the two rays I want you to draw for a concave mirror in this case. And in this case here, where these rays here intersect, sure there's a bunch of other rays, sure they still bounce off all these other, the mirror surface and all that, but wherever the rays intersect is actually where I'm going to form my image. In this case here, my image is always going to be sort of starting from the principal axis. This guy here is facing upwards, so sometimes you're going to draw a half arrow going up this way. In this case here, my image is actually going to be downwards, so that's where my brain thinks it's going to form. My image, a couple of things you can say, my image is actually inverted, it's actually upside down. When we get into the math in tomorrow's lesson here, we're going to have an HI that's negative. HI means the height of the image, but if it's negative, that negative just means we're flipped. And you notice the size of the image, unlike your height of the object being yay high for the candle, your image here is actually shrunken. So in this case here, we can say the word it's diminished. Basically, your image diminished. Basically, your HI here is smaller. HI is smaller than HO. The image that ends up forming, unlike the plane mirror, my height in is not my height out. It's actually tinier then. So again, without actually drawing any of the other rays, if you can draw these two rays, definitely that's all you would need. One important thing we're going to get into here is this one here is called a real image. And the reason why it's a real image is because there's actual light rays that actually bounce through it. This is the shiny side of the mirror. The light rays are sort of stuck on this left-hand side. The light rays will actually come through it here. A real image can actually be projected on a screen. So you notice we are on the real side. We are on the actual side of the mirror. We're not looking physically into that reflected world, that mirror side. What we're going to do is we're actually going to have, if I put a piece of paper up here, I can actually have a picture of an upside down candle actually reflecting on the surface on this side of the paper based on the way the light is actually bouncing off this mirror here. So because I'm able to project on screen, because it's actually made of real light rays, I can actually put up a piece of paper and I can see that picture of the candle. If I put the screen here too far back or too far out, I'll get a blurrier image because some of the light rays will bounce through, some of them won't. But in this case here, it should be perfectly in focus because all the light rays will tend to bounce through that point. And that'll be the same top of the image as we had the top of the object. This case here is more interesting here. This is like your spoon. If you look at a spoon really, really far away, you're going to see yourself as sort of upside down in the spoon. What's going to happen here is you can actually play around. The image is actually dependent on where I'm actually standing. Just for you to get a feel of this here, let's say we take the same concave mirror. This time, let's do focal point. Let's do center of curvature here. This time, I'm going to stand actually closer to the mirror. So there's my candle this time. You're going to draw the very same light rays. You're going to use a ruler, draw a parallel line. Parallel lines here will reflect through F. And then the line that hits the center of curvature, I would have to imagine that the sort of circle was nicer that way. In this case here, a line that would have been intersecting with the center of curvature, this one hits the angle perpendicular, it comes straight back, and it's going to actually end up creating my image that's actually behind me. Right? So from the principal axis, it is still upside down as earlier, but you see from the relative size, now that I'm not, earlier I was farther away from the center of curvature, now that I'm actually between center and the focus, what's going to happen? My image, I can still call it a real image because I have a real light ray. If I put a screen up here, I'm going to see a nice blown up picture of the candle. It's a real image, there's actual light rays that go through it. In this case here, some language, it's still going to be inverted, it's still going to be upside down, but this time it's magnified. This time it's actually bigger. This time your h of the image is actually bigger than the h of the object. Still a real image because a real light ray goes through it. Let's do one other example here. Still with a concave mirror. This one here is the more interesting type of mirror. We still have the center of curvature. We still have the focus. Let's say this time I'm right up against the spoon. You can do this the next time you're having cereal. You stare at the sort of the bendy side of the spoon. As you are really far away from the spoon, as you bring your spoon closer, you're going to see a difference in what happens to the mirror. In fact, when you're right up against the spoon, I draw the same ray diagram. I draw one line parallel, one line through the focus. I draw one line through the center of curvature. Sorry, it's not super clear here. Again, you have to use a ruler. You have to actually measure these sort of focal lines and whatnot. What's going to happen here is you're going to realize that on my real side, these light rays here actually end up separating. They're actually never going to meet on this side. But here, again, our brain plays tricks on us here. If it notices that there is a light ray that actually bends in this straight line here, it's going to imagine that this light here had come from something behind the scenes. The center curvature line also something behind the scenes. And where they actually intersect, the reason why I'm putting in dots here is these are not real light rays. Light rays can't actually travel through the mirror, but it's our brain playing tricks on us here. When we see light rays traveling at this angle, we believe that there's a candle inside the mirror that actually sent us these straight light rays. These are not real light rays here. So in this case here, we create what's called a virtual image. So it's not something, I can't put my screen physically into the side, inside the mirror. Again, we're not talking, we're walking around the mirror. We're saying physically inside the shininess of the mirror. It's a virtual image, but you can describe a couple things here. You can say, well, for this image, we're actually upright. We're actually going to be the correct orientation. We're not upside down. And also magnify, we're also bigger. So just drawing these two simple rays here, this was the type of mirror that actually depended on how far you're away. You can then figure out where your image is. I'm just going to end off this lesson here. Again, we're going to come back next lesson and talk about all the math of it, relating these terms, DI, DO, things like that. We're going to switch gears here and we're going to look at a convex mirror. A convex mirror here was your diverging mirror. It caused your light rays to actually bounce off. This one here, nicely, regardless of where I am relative to the focal point and the center curvature as we'll see, it actually will only have one situation. So we can make this ray diagram here nice and big. This time what's happening here is, here's our candle again. Our candle is emitting a whole bunch of light. This time I'm looking at the bulgy side of the mirror. I know from what we said earlier, the light rays end up just sort of bouncing off. Again, I have no time to actually go over all the different light rays. For a ray diagram, I'm just going to draw two rays, and where they intersect is where my image is going to form. This time, curiously though, we have our vertex still. That's when our mirror touched the principal axis. This time, the center of the circle is actually inside the mirror, and this time your focus is actually going to be inside. This is actually going to be the negative side of the mirror we're going to see in tomorrow's lesson. But here we go. For a ray diagram for a convex mirror, again, we're going to start off with a parallel ray. So a ray that comes in parallel flat to the principal axis. A parallel ray reflects as if it came from the virtual focus. Show you what this means here. Make sure you use a ruler here. Without a ruler, you're going to get it wrong. So I'm going to use a ruler. The light ray here is traveling from my candle. It's hitting the mirror sort of head on. Earlier we had said something that's parallel was supposed to go through the focus. Your real light ray cannot travel through the shininess of the mirror. But if we had a mirror image of it coming straight on, and if it would have bent parallel this way, we're going to be bending off as if the real light ray ends up traveling, diverges, it ends up separating, but it's as if it had come from the focal point. So that's the one light ray here. So I draw a solid line here. This is a real light ray here. These dashed lines here is just our brain playing tricks on us here. If I see a light ray end up going off at that angle, I think it had gone through that focal point. And the second ray that we ended up drawing here was one that was going through the center curvature. So again, we're going to say here, a ray through C. I'm going to say remains, here's just some language to it. They say undeviated. If you deviate, you sort of go one direction or the other direction. If I'm undeviated, I basically come back exactly the way I came. So in this case here, I'm going to send in a light ray. I'm going to send in one ray here, use a ruler here. It's supposed to hit C straight on. a ray here hitting C straight on would be a sort of 0 degree in, 0 degree out. It's going to come back exactly the way it came. Again, you're going to see a problem. On the real side, these light rays here diverge. They're never going to come together. But our brain, again, silly enough, plays tricks on us here. It's as if there was an intersection point. It's as if there is going to be an image. When you look at the bulgy side of the mirror, you're actually going to see the image. First thing, it's going to be a virtual image. These are not real images. It's not like you can put your screen inside the shininess of the mirror. So real image, but it is upright. It is sort of right side up. It's still standing upwards. And it is actually diminished. It is actually smaller than what we see. And what you're going to find is when you do your practice for this one, regardless of how close I am, regardless of sort of where I would be relative to where the focal or where the center of curvature may have been, sort of mirror image on this side here, we're going to still have the intersection always on the other side. All right? So I'm going to end off the lesson that way. We'll do this on a simulation in the next lesson and then introduce some of the math. All right? If you have any questions, just let me know. Thanks, guys.